atoms, ions, and molecules. Oh my. And we're going to do a little on the periodic table. So let's start with the basics. What is an atom? An atom is the smallest particle of an element that retains its chemical properties. Now there are things that make up an atom. An atom is composed of a nucleus and an electron cloud. The nucleus is extraordinarily dense and contains almost 98%, well more than 98% of the mass of the atom. It contains protons, which are positively charged, and those determine the identity of the atom, or the atomic number. And we give this the letter Z. The nucleus also contains neutrons, which have no charge, and when you add to them the number of protons, you get the mass of the atom. And changing numbers of neutrons give us what are called isotopes, and we'll talk about those in a few minutes. Electrons have no mass, and they're used in bonding. Because they're on the outside of the atom, they can be easily added or removed or even shared with other atoms. You can tell what an atom is by writing it in isotope notation. In isotope notation, you write the chemical symbol, and above the chemical symbol you write the mass, and below that you write the atomic number. So the formula is A, which is the mass, over Z, which is the nuclear charge, or the number of protons, and then just the atomic symbol. So for example, for krypton here, krypton, this is krypton 38, because it has or 78, because it has a mass of 78. It's krypton because it has 36 protons. Element M here has 33 protons. So if you look at your periodic table, element 33, or element with the atomic number of 33, is arsenic. So this is arsenic 75. What is an isotope? An isotope is an atom with the same number of, or with the same atomic number, so the same number of protons, but different numbers of neutrons, and therefore the mass is different. We use isotopes to determine the average atomic mass of an element. It's the reason why the masses on the periodic table are decimal points, because they are a weighted average. To determine the average atomic mass, you take the percent abundance, or how often that particular isotope occurs in a sample, and multiply it by its mass. You add to it the percent abundance of another isotope times its mass, plus the percent abundance of a third times its mass, and so on and so forth until you have accounted for all of the isotopes. The greater the percent abundance, the greater the effect that isotope has on its mass. So for example, hydrogen has a mass of 1.0079, which means if I was going to guess the most common isotope of hydrogen, I would probably guess hydrogen 1. There are other forms of hydrogen. There's hydrogen 2, which we call deuterium. That's hydrogen with 1 neutron, and hydrogen with 3 neutrons, in case you're ever on Jeopardy, is called tritium. Most elements have at least 2 stable isotopes, and there are only a handful, well 3 that I know of, that have only 1 isotope, 1 stable isotope. A molecule is the smallest unit of a compound that retains that the chemical characteristics of that compound. Molecules are held together by chemical bonds. These are forces of attraction that hold the atoms of a molecule together. So therefore, it's the energy that's holding them together. The weaker of these two is covalent bonds. A covalent bond is when a metal and a nonmetal form a bond, and they share electrons. This sharing makes these independent units called molecules. You can write a chemical bond in either a molecular or structural formula. A molecular formula shows each atom or each molecule and just uses the symbols and subscripts to denote how many of each one there are. So for example, these two down here, methane and ethane, it shows CH4 and C2H6 are the molecular formulas. Structural formulas show bonds between each element with lines, and it may not indicate the shape. For example, if you were in baby chem last year, you now know that methane, CH4, has a tetrahedral shape. If you looked at this on the piece of paper, though, you might say that's square planar because it's all laying flat on the page. However, later in the year, we will go over structural formulas and line structures in much more engrossing detail. But just know that a structural formula shows lines, shows bonds as lines, and does not necessarily indicate shape. The stronger of the two bonds are ionic bonds. Ionic bonds form when electrons are lost or gained by the elements in the bond. The element or atom that loses electrons and therefore becomes positive is called the cation. The element that gains those electrons, or the atom that gains those electrons, is called the anion. You can have what are called polyatomic ions. These are units of atoms, so multiple atoms together, such as ammonium, NH4, has a positive charge. That's a polyatomic cation. Or you could have an anion, a polyatomic anion, such as sulfate, SO4 2-. At the beginning of the year, I gave you a list of 14 polyatomic ions that you are to memorize. So this is when we're going to start getting into them, when we start talking about ionic bonds. This positive attraction, or the attraction between the positive and negative, the cation and the anion, is what form ionic bonds. Ionic bonds, being the strongest, have extremely strong intermolecular forces, extremely strong attractions between those molecules, and because of this, they will typically form solids. The strength, we're going to come back to that picture. The strength of that attraction is related to a Coulombic force, which is proportional to the charge of the first ion times the charge of the second divided by the distance between them. This will come up more and more when we talk about intermolecular forces. When an ionic bond forms, they do not form one sodium to one chlorine like you would expect from sodium chloride. They actually form ionic solids or crystalline lattices, and the simplest ratio of one element to another is called the formula unit. So whenever you write an ionic compound's formula, you're actually writing the formula unit of that compound. You're not necessarily writing its exact ratio of one element to another. Well, you're writing the exact ratio, but you are not writing the exact number of atoms or of elements to one to another, like you are when you are doing covalent bonds. So we're going to end this video with a little bit on the periodic table. It's going to be a very basic run through of the periodic table. You will expect to be much more engrossing detail as we progress through the year. But this is the periodic table. This is a representation of the one you get when you get your periodic table from the AP exam, with the exception of I've added the charges up here. Because for the most part, all of the group, and you call the columns groups or families, have the same charges. For example, all of group 1 gets a +1 charge. All of group 2 gets a +2 charge. Group 3 typically gets a +3 charge. Group 4 plus or minus 4. Nitrogen and phosphorus typically get a -3. The chalcogens, or group 16, typically get a -2. The halogens all get a -1. And this last column over here, notice how it has no charge. It's because these are the noble gases. Elements gain or lose electrons to have structures similar to the noble gases, to have electrons in the same places, quote-unquote, as the noble gases. So you can also use the noble gases to determine what the charge of something, or determine a generality for the charge of something. Halogens will gain 1 electron. Alkaline metals will lose 1 electron. As I said, columns are called families or groups. Rows are called periods. Now, the periodic table is broken into 3 categories. You have metals, nonmetals, and metalloids. So let's talk about metals, because metals make up the vast majority of the periodic table. They are pretty much everything on the left side of the periodic table, from group 13 over, and including some of the ones under here, such as tin and bismuth. Everything over, including down here, these are called the rare earth metals, and they are metals. Metals, as you can probably guess, conduct electricity. We'll talk about why in just a moment. But they are malleable, which means you can hit them with a hammer and they will move and shape themselves. They can be hammered into thin sheets. They are ductile, meaning they can be pulled into thin wires. And they have luster. They are typically very shiny. They're described as a cation because they have a positively charged nucleus in a sea of electrons, because there's a lot of electrons floating around them. This is what gives them their ability to be malleable and ductile. It also what allows them to conduct electricity. Metals also will corrode or tarnish or oxidize. They readily form oxides, or they'll rust. Nonmetals are everything on the right side of the periodic table. All of these all through here, from carbon, phosphorus, selenium, iodine, and radon up. Those are the nonmetals. Nonmetals are pretty much the opposite of metals. They're brittle, meaning they'll fall apart in your hands if they form a solid. They're typically dull when they form a solid, whereas compared to metals are shiny. And they all form anions, meaning they will readily gain electrons and therefore become more negative. Now the ones between the two, between metals and nonmetals, boron, silicon, astatine, tellurium, and hold on. Sorry, this is astatine, that's arsenic. And some of the ones around them, such as germanium, antimony, polonium, those are called metalloids. They have properties of both metals and nonmetals. They can conduct electricity. They're typically not brittle, they are brittle. This is a typo on here. Metalloids are typically brittle, however they can be shiny. For example, silicone is a very, very shiny metal. It's on the bottom of your CDs. It's what gives that shiny look. But it will fall apart readily in your hands. Now the families of elements that rise up out of the periodic table, the ones that are high up here above this dip, are called representative elements, and it's because they represent the greatest variation of the periodic table. This dip in the center, including the rare earth metals, are called transition metals because they transition between the alkaline metals and the alkaline earth metals and the nonmetals. Typically, typically transition metals get a +2 charge when they form an ion, and it's because they'll lose the 2 electrons from this outer edge. We'll talk about why later in the year. However, for right now, you can just generality say they will be a +2. Also, it's because they have d electrons, they will form colored solutions, with the exception of zinc's family. Zinc, cadmium, and mercury typically do not form colored solutions, but everything else in here will form a nice, pretty colored solution. For example, chromium is pretty pink or purple, and iron, you can guess, would be red. Copper is a blue or green. So we'll be going over that later as well. So there's a few families you do need to know from the periodic table. It's important that you know their names. Alkaline metals are this first group, group 1A, or group 1 on the periodic table. Alkaline earth metals are group 2A, or just group 2. They're called alkaline because in solution they form basic solutions. They form, basic solutions. One way to describe that. Group 16, so oxygen's family, or 6A, are called chalcogens. You will very rarely see that on the AP exam, but just FYI, they call these chalcogens. One you'll definitely see on the AP exam are halogens. When they form ions, they're called halides. Halogens are group 17A. They are one of the most reactive of elements, or most reactive family. They are never found on their own. They're always in some sort of compound in nature. And lastly, group 18A, or group 18, or 8A, is the noble gases. They are extremely inert. With very few exceptions, they never form bonds. Xenon, only in the laboratory under extreme stresses, will form a bond. But it's because they are so stable. You can also use the periodic table to determine the number of valence electrons. These are the electrons on the outermost edge of the atom. And it has to do with the last number in the column, or in the family, of the representative elements. So the last number in group 1 is 1. So valence electrons for group 1 is 1, or R1. Let's say group 14, or group 4A, carbon's family, has 4 valence electrons. Group 17, the halogens, have 7 valence electrons. And that's about all you really need to know for the periodic table.